Hey everyone, welcome back to CSE 373. Before I introduce the content for today, I want to quickly mention I did actually just get some braces. It's the invisible kind, you can't quite see, but it does impact my ability to talk because there's now plastic in my mouth that wasn't there before. So if my voice sounds a little bit different, it's just a temporary thing, I think, but I just wanted to mention that in case you heard. So today I want to introduce the traveling salesperson problem. And the traveling salesperson problem is a very popular problem that computer scientists have tried to solve. And I want to talk about kind of what that problem is, how are we trying to solve it, and the reason I'm bringing this up right now is it's a really interesting application of all this graph stuff we've been talking about. And there recently was a really big breakthrough in this problem that came from the Allen School. And so I wanted to kind of set up some context for what that was trying to do. And now that you understand a lot of this graph stuff, you can understand a lot of current research in CS. Now, a lot of the details might not make sense. They don't always make sense to me either. But it is kind of cool to appreciate and understand at a high level what current work is trying to do. So I want to mention the first thing off the bat is that this set of videos are going to be optional. So they're not part of the core learning objectives for the course. So I don't have any concrete learning objectives for these videos. I really want you to just sit back and see something cool from what we've been using. So I'll show you how to apply the things we've learned so far, but I don't have any expectation of concrete skills for you to pick up from this. So I'm going to start by outlining kind of what this traveling salesperson problem is, and then I'll explain algorithms to solve it. So congrats, you just got hired as the new super delivery person at the USPS. Your first job is to deliver mail all across the country. Since I guess they're probably like firing all of their mail people, you now get the sole job of delivering all mail across the country. So your task as a savvy computer scientist is to figure out, okay, well, you need to go travel around the entire country, go visit all of the big cities. And you want to travel in such a way that saves you time. So maybe, for example, trying to find an ordering of all of the cities to visit that minimizes your total trip length. Now, that goal, an ordering a visit to visit all the cities such that the total distance of your trip is minimized, is the goal of the traveling salesperson problem. You'll sometimes hear it called the traveling salesman problem. I feel like that's an unnecessary gendering of occupation. So I call it traveling salesperson, but more commonly we use yet another abbreviation for things related to graphs, and we call it TSP for short. Now, this goal sounds nice in theory, but it can be pretty challenging to try to meet that goal. For example, it's not always clear how to tell, just looking at a graph, that the shortest path isn't like bouncing from one side of the country to the other. Now, like intuitively from our perspective, that should be the case, that you'd probably visit nearby cities first. But it's really hard to describe that to an algorithm. So a huge problem we're going to run into is there are a lot of possible paths to explore that complete this cycle around the city or around the country. Go ahead, try it out. Take a minute and pause this video. Here is a picture of a graph. I want you to try telling me what's the cycle or what's the path to visit all these vertices that has minimum weight. Go ahead and pause, try it out. I don't even have an answer for you. I did not spend the time trying to figure this out because it's really, really tough. It is not obvious at all how to do this problem. So a bit more formally of what this problem is you're given an undirected weighted graph G, and we commonly will assume that G is complete, meaning it's pairwise connected, but that's not always a necessary requirement. And we're going to output a path of minimum total cost from some start vertex that visits every node in the graph exactly once. Now, the start vertex, we're going to make this a cycle. So the start vertex will be visited twice, but that's the only one. So you start and end at the start vertex. Sometimes people call this the Hamiltonian cycle of minimum weight. There's a lot of fancy graph terms that use the names of old mathematicians. So Hamiltonian cycle is just another term for this, but we're not going to worry about that terminology. Now, this is the statement of the problem. And the question is, given this graph, how do you find this path? Now, before we talk about algorithms, I want to make one aside. There are many, many, many variations of this TSP problem. All of them have different flavors, different assumptions. One of the ones that receives a lot of attention is this one called Metric TSP, which we're going to talk about today. So what Metric TSP is just a particular type of traveling salesman problem where the graph we're working on kind of follows an extra set of rules. It's called the metric requirement. And really at a high level, it's just saying that the edge weights make sense. Like if this graph is supposed to represent like distances between cities, then the edge weights should behave reasonably, meaning that all of the edge weights are non-negative, except if it's an edge from a city to itself, then it should be distance 0. And then we also say that the edge weights should obey the triangle inequality, which really is just saying that the distance between A and C should be less than taking a longer path around. So going from A to B to B to C. This is commonly known as the phrase the hypotenuse is shorter than the sum of its sides. But this is just like something that needs to be true in order to behave the normal rules of space. And so we usually have this extra assumption in terms of a lot of the work that's being done here, that these edge weights aren't completely arbitrary. This is not super, super important to stress because there are lots of different algorithms for different assumptions, but all of the work I'm going to be talking about today is kind of really focused on this one particular instance where the graph is representing cities and distances make sense. So your first idea of trying to do something like this would be something Dijkstra's probably, right? Finding the shortest path in a graph, let's use Dijkstra's. So maybe a proposed algorithm would be something like pick some start vertex V, run Dijkstra's on V to get the shortest path tree, and then do something with that shortest path tree, and then maybe something else. Now, it's not clear how to take this shortest path tree and turn it into this cycle that visits every node in the graph. You might have an idea of where to start. Like maybe you could say like, oh, go from A to B to D because that was part of the shortest path tree from A. But then now you're at D, this shortest path tree doesn't really tell you anything about how to explore from D. So this thing gets really complicated really fast, even for simple graphs. So it turns out that all of the exact solutions that we know are really inefficient. So for example, the simplest solution you can actually come up with is just enumerate every possible path and then see which one has minimum cost. Unfortunately, this will take something like V factorial time. Factorial is this operation that's like when you talk about n factorial, it's n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. That is a huge runtime. It's worse than exponential. So this is going to be very, very slow. And it turns out even the much cleverer algorithms, ones that use these techniques called branch and bound and other fancier kind of enumeration techniques, they still kind of result in this kind of choose, explore, unchoose pattern of recursive backtracking. So they also still take something like exponential time, even in the fastest algorithms. And exponential is not good, right? Most computer scientists think that we can't beat this exponential time. And exponential is bad because even for moderate-sized inputs, it could take years and years to run. So there's a not super recent, but somewhat recent study where they tried to run the algorithm for the traveling salesperson problem on a graph with 85,000 cities, which is not like the largest number of cities possible, but it's a decent amount. And that would have taken something like 130 years to compute. But so if you were trying to run this on something even with even more cities, you can imagine that this would take lifetimes upon lifetimes to complete. Now, computer scientists are relatively pessimistic that a faster algorithm, namely a polynomial time algorithm, something that's like v squared or v cubed, they aren't very optimistic that this thing exists. I can't really explain why right now. This is going to be something we're going to talk about more on Monday. So we're going to talk about this thing called P versus NP and talk about what that means and why computer scientists are generally pretty pessimistic, but don't technically know yet that there is no faster algorithm to solve this problem. So if we're not going to be able to solve it exactly, this doesn't mean it's the end of the story. What we'll talk about in the next couple videos is kind of a slightly different approach to solving this, which is rather than trying to solve an exact solution, try to approximate it. Find a solution that's good enough without being too wrong. And we'll talk about that in our next video.